Hello, and welcome to today's WJE webinar, Investigating and Repairing Common Issues in Wood-Framed Buildings. My name is Liz Pimper, and I'll be your moderator. During the next hour, engineers Lorintz Gleich, Steve Mayhew, and Paul Parfitt will explore several of the most common issues with wood frame construction and discuss how they are investigated and addressed. This presentation is copyrighted by West Janney Elster Associates. And now I will turn it over to Paul to get us started. Paul?
All right, thank you, Liz. So the first couple of slides, we're just going to do some required ones here, learning objectives, a brief review of kind of what we're going to be trying to teach everyone today. Next slide is going to be on the agenda. Again, just what we're going to be covering from a topic perspective as we work through this presentation. So we're going to jump right into kind of typical wood construction. So obviously, hopefully we're all here because wood frame construction remains a dominant material in the United States. As recently as 2015, as much as 87% of multi-unit construction, as well as over 90% of single-family homes are constructed with the wood frame construction. For this presentation, we're going to predominantly focus on those low to mid-rise structures, so typically podium-style apartments, condos, hotels, and light commercial construction that are constructed with typical dimensioned lumber framing. We may talk about proprietary wood structural products such as glulam or LVL, but we're not going to really dive deep into those products right now. So it's important that even though we're talking about common issues in wood construction, that we highlight some of the benefits, right? Because this is one of the most dominant building materials in single and multifamily homes, 4 stories and under. So things like cost effectiveness, sustainability, workability, thermal benefits, as well as speedy construction, so getting us shorter schedules and faster occupancy are all important aspects of why this is a dominant building material. Some key properties to consider when doing building design and performance for these types of structures. We're going to talk a little bit about decay resistance, building behavior, so dimensional changes like shrinkage and contracting of finishes, and then also the overall behavior of wood itself, so things like the structural capacity based on the orientation of fibers, as well as capacity effects from load duration that Steve will jump into in a little bit here. So Steve's going to talk a little bit about wood properties.
All right, thank you, Paul. So before we get into the common issues, to better understand some of these concepts discussed later, we're first going to go over some of the basics of wood to better understand both its structure and how it behaves. While wood is a wonderful building materials for many reasons, as Paul mentioned, it's also rather unique. Wood is a natural material and it contains natural defects, and its mechanical properties and dimensional behavior are affected by its moisture content. We're going to briefly discuss the following topics: wood strength and stiffness properties, the effect of the duration of load on strength properties, and the effect of moisture content on strength, stiffness, and dimensional properties. Mechanical properties of wood vary both with each species and within each species. Clear straight-grained wood is the strongest, while natural defects occurring within the wood reduce its strength. Wood strength is decreased by the following factors. First is slope of grain. The image to the right shows checks that are visible on the wood surface, and those can be used to identify the slope of grain. We can see in this sample there's a high slope of grain that's present in the member. Knots also result in a grain deviation, also resulting in a high slope of grain, thus decreasing the strength of the member. And lastly, splits, checks, and shakes affect the shear capacity of a member. However, it's good to know that the grading rules do allow for most of these types of defects by incorporating a built-in 50% reduction in the shear capacity. The bending strength and stiffness are greatest when the stresses are induced parallel to the wood grain. The example on this slide shows a simple beam and bending resulting from a point load applied at the mid-span of the beam. The point load results in compression stresses along the upper portion of the beam and tension stresses along the lower portion. Beams with a slope of grain as parallel to the induced stress have the highest potential strength capacity. However, if a naturally occurring defect is present within the member, such as a knot shown along the bottom piece of the lumber, the resulting stress occurs at an angle to the grain thus reducing the strength capacity. The bearing capacity of wood is much higher when loaded parallel as compared to perpendicular to the grain. The image at the bottom left shows an as-constructed detail where multiple plates were used to support a 4-ply LVL beam at an interior bearing. Visible crushing occurred in the wood plates that could be seen in the location shown by the red arrow. In addition, the use of multiple stacked plates for bearing is not recommended due to the potential for problematic shrinkage, which will be discussed in more detail later by Lorintz. The image to the bottom right shows a repair of this condition with parallel MPSL installed vertically such that the compressive load from the beam acts parallel to the wood grain, or basically through its strength. Wood is also different than most structural materials in that it will exhibit higher strength when resisting shorter duration of loads. So as the graph on the right shows, as the duration of load increases, the allowable load decreases. And this effect is accounted for during the design of wood members by utilizing the factors shown here for each type of load, depending on the relative expected duration. Loads with the shortest expected duration, such as wind and seismic loads, have the largest increase of 1.6, while permanent dead loads have a 10% decrease in the allowable load. Moisture in wood exists in two forms. It can be present as bound water, or basically water that is chemically bound within the cell walls, and unbound water, or water that is held in the capillary voids located between the cell walls. This distinction between the two is important because the influence that the bound water has on the strength, stiffness, and the dimensions of a wood member. The moisture content at which the wood properties and dimensions do not continue to change is commonly referred to as the fiber saturation point, or short FSP. This occurs around the point where the cell walls are saturated and can no longer hold more water. And this is typically around 30% for most wood species, but that does change a couple of percentage points depending on the wood type. And wood will absorb moisture vapor from the air, and the moisture content will eventually equilibrate if the temperature and relative humidity are held constant for a sufficient amount of time. And this is referred to as the equilibrium moisture content. All right, now we'll briefly discuss the effects of moisture on the strength and stiffness of wood. So below the fiber saturation point, the wood properties will change with changes in moisture content. And as the moisture content increases, the strength and stiffness will decrease. Stiffness decreases approximately 25% until reaching fiber saturation when there are no additional changes. And when dried, some residual strength losses are likely, but they're generally small. So below the fiber saturation point, wood changes volume because the volume of each cell wall changes with the amount of bound water. And very small changes occur along the length of the wood, and therefore dimensional change in this orientation is sometimes ignored. So because wood primarily grows and shrinks in its width and thickness, most vertical movement occurs within the wood top plates, bottom plates, and within the floor lines. The image at the right shows the zone of movement as the yellow area. More shrinkage will occur if the building is allowed to get wet during construction, increasing the starting moisture content of the wood prior to dry-in of the building. The example here, taken from a Woodworks article, Accommodating Shrinkage in Multi-Story Wood Frame Structures, shows a calculation of shrinkage for a conventionally framed floor system with using dimension lumber when going from approximately 19% moisture content down to 10% moisture content through drying after putting on the roof, exterior cladding, weather barrier, etc., and assuming dimension lumber is used for the floor structure. And when doing this calculation, we come up with approximately 5/16 of an inch of shrinkage right in the zone of movement area. All right, so a little bit about decay. All of these are needed when talking about decay. We need all four: oxygen, a sufficient amount of moisture, a food source, and suitable temperatures. So 2 of these 4 components can be controlled on most projects. We can use preservative treatments to poison the food source, or we can use a naturally durable species, which contains extractives that serve a similar purpose. We can also limit the moisture content of the wood by keeping it protected from liquid water. I do want to note that fiber saturation is required to initiate decay fungi growth, which is approximately, as I said, 30% moisture content, while lower moisture contents can allow decay to continue to grow. And decay fungi has a significant impact on strength of the wood because it consumes the lignin and or cellulose of the wood cell. The photos on the right show the effects of brown and white rot on wood. Brown rot results in cracks perpendicular to the grain, much like charring, and white rot leaves a stringy residue after the cells are consumed. But both of these result in softening of the wood and a significant loss of wood strength. And then similar to decay, wet wood increases the potential for insect-related damage. And we can use similar techniques to keep insect damage in check. We can keep the wood in a dry condition, and we can use insecticides to poison the wood. And I did want to note that most wood preservatives serve as both a fungicide to resist decay and an insecticide to resist wood-consuming insects. All right, I'm going to hand it over to Paul to talk about some common issues.
All right, so when we talk about common issues affecting construction performance and service life longevity, we're going to kind of bucket these into about 4 main categories. One being differential movement, another being excessive floor deflections, another being decay, and then a last one kind of covering all the other issues that we might encounter. We're going to take these common issues and break them down into 3 major causations. So we're going to have design deficiencies, which we're going to highlight throughout the presentation with a blue icon, construction deficiencies, which we'll highlight through an orange icon, and the end user or in-service conditions and maintenance practices, which we will highlight with a green icon. It's important to note that wood construction varies by region. So for example, in high seismic regions, we might have different design and construction requirements that lead to different types of deficiencies. Similarly, in environmental conditions might also vary. So a decay might be more of a concern in the Pacific Northwest than it might be in an arid region like Arizona. And then we also have architectural trends that are going to differ across the country. So EIFS versus stucco versus brick on a facade, or perhaps concrete balcony toppings versus a wood deck topping on a balcony, are all going to have different detailing requirements that might lead to different or the same issues. So jumping into some common issues, excessive floor deflection. This is more going to be pertaining to a end user condition, and what they should be looking out for, whether that be an owner or a maintenance personnel, would be things like cracking and sagging of drywall, nail popping. Maybe they had an actual drywall panel collapse, or they're getting reported uneven flooring from a tenant. Also things like cabinet and countertop separations from walls and other finishes. So examples of cracking and sagging drywall, what you're going to look for is typically going to be some straight orthogonal cracking, likely at panel-to-panel drywall joints. These are typically going to occur in the middle of the room or around the midspan of the truss. Some other not as dramatic incidences might be nail popping. So these are going to be small dimples that occur in regular spacing intervals across the drywall panels. And you might get an quote extreme condition where you have some drywall mud that actually has spalled off and you're exposing the nail head or things like that. You might also get tenants that are reporting uneven flooring, whether they're tripping across the floor or maybe they've got drainage issues in certain areas. And you also will have potentially cabinet and countertop separation. So as a floor deflects, it might want to rotate the cabinets in the kitchen, say, and as that rotates, those are going to want to pull the countertops away from the wall or potentially pull the countertop away from another one, and you'll get these cracks or gaps that start to form. So when we get called for these types of problems, one of the initial assessment investigation things we're going to want to do is obviously do a visual survey of an individual unit or units to document any distress patterns similar to what we just described above. Inspection openings might be necessary to document the conditions of the structural elements behind the ceiling. So this is going to be a rather invasive and destructive way to do that assessment. And for some of the examples we're going to be talking about through the next few slides here, we're going to focus on metal plate connected roof and floor trusses, because these are one of the more common systems we see that require these types of inspection and surveys when we get excessive deflection reports that we come out and look at. So when we get out to those sites, one of the first things we would like to do is probably do a floor deflection survey. So we can do something as simple as performing a ball rolling test, where we're going to actually place a ball on the floor and watch it roll to the low point in the floor. That'll tell us exactly where that deflection is. The other thing we might want to do is maybe just a simple walking test. So we're going to shuffle across the floor with our feet, try to perceive exactly where the deflections might be. And then we get into some of the more technical ways to do some surveying. We do data gathering with either a laser scan or a digital level to get us a map in a grid-like pattern of where those hot spots are or lower depressions, which is going to help guide the investigation. Because most times what we might have is higher instances of damage or deficiencies in those lowest points on the floor. Some of the common causes from excessive floor deflection could be a combination of things, but we're going to tailor them into 4 categories: overloading, structural support, truss layouts and orientation, and overall building behavior and differential movement in heights. So from an overloading perspective, from service and construction observations, we could have objects and materials that might just be too heavy. So for example, if a contractor is placing pallets of materials in an area that they shouldn't, and it's getting too heavy for that floor. The other thing we get a lot of calls for is dynamic loading from things like parties, rhythmic bouncing and dancing. And studies have shown that these dynamic loads can actually lead to loading over twice that of the static design load for those areas. And while some things like common areas and areas that are made for congregating will have a higher static design load that should accommodate some of that dynamic loading, individual units don't. So ASCE 7 also does not include any type of dynamic amplification requirements, such as dancing and rhythmic bouncing, for things like inside of individual units, which also have those lower static design loads. So that's something to consider. Structural support from a construction standpoint, this could be something as simple as an unsupported or inadequately supported wall. Maybe the contractor forgot a squash block in an area where a wall is coming down on a truss. We also have missing, damaged, or poorly fabricated structural components. So for example, in the images down below on the left, this is where a contractor had a forklift come through and damage a truss as they were installing it when they were picking it up. The other 2 images in the middle and on the right are from a manufacturing standpoint. So we have inadequate plate engagement due to wane of the wood, which is a natural chamfering that wood sees that got installed, which limits the amount of teeth that got engaged in the plate. And the image on the right is partial plate embedment. So this is when the manufacturer's machine actually does not press the plate fully into the wood member, and therefore we get a gap where it's not fully pressed. And Truss Plate Institute actually has a graph or a chart that shows that you can have up to a 3/32 of an inch gap from this plate to the member, but you do get a reduction of up to 60% of its capacity when you have that 3/32 gap. Anything larger than that, and you basically get a 0 capacity out of that truss plate connector for that specific element when it's not embedded properly. Structural support from a design perspective, this could be as simple as just an inadequate design. So as part of that investigation, one thing we'll want to do is verify that the truss, as built and as designed, was designed in accordance with the code prescribed loads for that scenario. So if we're lucky enough to have shop drawings, we might use them for the geometry, or we might have to go out and physically measure the whole truss to get that geometry, plug that into our analysis, and figure out whether or not the design was adequate. A lot of trusses also have a very specific location and layout that they need to be installed on because they're not always symmetrical. So we can get things like incorrect joist locations or truss orientations that are actually flipped from where they're supposed to be. In this example on the left, we had truss 219 and 220 that were flip-flopped, and that became an issue because this diagonal wall is a load-bearing wall, and that actually led to the loading condition or the bearing location to be offset by about 2 feet in that situation. So when we have unintentional bearing, what this is going to do is drive unintentional forces into the members themselves, which can lead to an overload of the member and or the plate. And for this example, the analysis we performed, the as-designed truss was capable of sustaining the regular code prescribed design loads. However, the as-built condition led to a overstress of about 80% on those members, along with some unintended load reversals. And our analysis actually lined up with our field surveys for this one. For example, we actually had more distress and problems in the area that the analysis determined was going to be overstressed. So that was a good verification of what we're actually seeing there. Differential movement from a design and construction standpoint, we could have things like construction tolerances that may have a wall that was cut slightly at different height than the other bearing wall, so we're going to get a differential in height there. We could also have things like frame shrinkage. Designers need to account for that frame shrinkage, and if there's a truss bearing on an exterior wall that might have more shrinkage than an interior bearing location, you're going to get that differential in height between the two. And then also things like floor support layout. So not every floor might be identical. And the condition we have here in the example, we have a full height load-bearing wall that's adjacent to two long-span trusses. And obviously, the long-span trusses are going to want to deflect at a different rate than the much stiffer load-bearing wall. And we're going to get differentials in height there that might be perceived as potentially a deflection that's causing an issue when it's really just a stiffness thing. So what do we do with repairs when we have these damaged floor trusses where we've got metal plate connectors that have failed or elements that have been fractured? Well, the repair is going to be rather simple. It's going to be mostly a plywood gusset plate that we add to one or both sides of the truss that's fastened with structural screws. And it's important that we have an analysis performed so that we can identify these critical connections and components, whether or not we have redundancy in the system, because we're not always going to be able to access those points all the time. So that's always something to be considerate of. Jacking of trusses might also be required to, one, not only bring the floor back into a level of tolerance for the end user, but also a lot of times when we have excessive deflections and failed plate connectors, we'll have gaps that form between the members at the joints, such as the image in the upper left, that we have to close back up. It's important to make sure that the contractor knows what they're doing here, because you can have unintended damage if the contractor is jacking the trusses up in the wrong manner or they do it too quickly and so on. When we're dealing with repairs, another consideration we might need to take into account are ceiling plenums. And a lot of these multi-unit houses are going to be full of mechanical equipment and utilities. So we can't always get to every connection that we may want to repair, or we might have a conflict. So it's important for the designer to make sure they're communicating with the contractor so that we can identify those conflicts early and address them. For example, in the photo in the middle, we had a sprinkler line that was in conflict with one of the repairs we had designed, and the contractor decided to modify that in the field. And when the engineer came out to do their final inspection, they noted this one, and that contractor actually had to remove this connection and redo it because they cut off the plate gusset in the wrong location. So with excessive floor deflection, some tips we can have for the different categories here. So during design, make sure you're accounting for anticipated loading conditions. This can be things like dynamic loading, especially if you're talking about student housing, where this dynamic loading seems to be more of a problem. Also, things like differential movement, making sure shrinkage and thermal movement are accounted for in the design. And then also communicating with the contractor, make sure we're addressing field conflicts quickly and effectively. From a construction perspective, don't overload the spaces with materials, making sure your layout of your truss placements and orientations are accurate, especially when you're dealing with oddly shaped rooms or eccentric bearing wall locations. Also making sure your construction tolerances are correct, so wall heights, placements, things like that. And then same thing during repairs or other field modifications, making sure you're communicating with the design team early and often to address those things like those conflicts. From a service perspective, performing regular visual surveys during either tenant turnover or regular maintenance, such as replacing smoke detectors, to look for signs of deflection that could be problematic should be done. And then also, again, considering the effects of dynamic loading on parties and individual tenant units, such as student housing, and considering things like potentially limiting the occupancy size or even party sizes as part of a lease agreement for those. Next, Lawrence is going to talk about some differential movement.
Hey, good afternoon, everyone. Differential movement is an issue involving the movement of different building components or systems which interact and result in distress or damage to a building. During this presentation, when we mention wood framing movement, it's intended to include both the wood shrinkage plus the consolidation of construction gaps between the framing members themselves. Remember that these buildings consist of many cut and stacked framing members to achieve each level over the height of the building. Differential movement can occur between the wood framing interacting with MEP lines inside the walls, which do not experience the same shrinkage or settlement. Or when there are other adjacent structural framing materials utilized in addition to the wood framing. Or when combined with volumetric expansion of a brick veneer. We're going to look a little closer at each of these. Wood framing movement is cumulative over the height of these multi-story buildings. For the case of a PVC drain and vent line system constructed inside the walls, the differential movement between the wall framing and the piping increases at each level. When the differential movement is not accounted for appropriately, the pipes can interact with stud or wall penetrations, build up strain, and can cause breaks as shown in these figures. Also in the left photo, notice the red-colored fire stop sealant installed at the pipe to floor penetration, which has now failed due to the differential movement between the framing and the piping system. For those that are not aware, brick veneers will typically expand in service for the first few years as it absorbs moisture. When the brick expansion is combined with the downward framing movement at exterior walls, it can result in performance issues for windows, making them inoperable. In the case of the photos on the left and in the middle, the windowsill compressed the window frame, resulting in a window that could no longer lock, nor could it be operable. Additionally, this interaction can result in negative slope of windowsills and even the flashing as shown on the right, making them both prone to hold water instead of shedding it away from the building. Here's a case study published by our colleagues Zeno Martin and Eric Anderson, where steel framing was used to support the exterior edge of balconies. The interior edge of the balconies are supported by the wood-framed exterior walls. While these balconies may have been constructed with appropriate positive slope to drain towards the exterior, it clearly did not account for the framing movement, which occurred after construction and resulted in back-pitched balconies and ponding water. The ponding water led to moisture intrusion and wood decay. Here's another example with concrete framing adjacent to wood framing. This case involved a fire separation wall, which included a concrete wall panel system with wood frame walls on either side. A few years after occupancy, the owner reported humps that had developed in the hallways and at the roof level. The humps aligned with the firewalls, where the wood framing movement had occurred, but the concrete wall panels did not move nearly as much. The fire doors could not function properly, so they had to be reinstalled. At the roof level, the hump shown in the orange dashed line has prevented the roof from draining properly. As you'll notice, the drain and scupper is to the left of the orange line, and so the water ponded on the roof. Woodworks has a good publication that we've already referenced, and we'll show it here, appropriately titled Accommodating Shrinkage in Multi-Framed Wood Frame Construction. The publication discusses the conditions we're presenting today, as well as several other differential movement cases. It is also listed in the presentation's recommended references. Okay, now that we have a baseline understanding for what differential movement is, now let's discuss what to do about it in these multi-story wood-framed buildings. First, the design team, typically a structural engineer, should figure out the magnitude of the anticipated framing movement based on the project's specific framing design, such that the other design partners and the construction team can make sure to accommodate for it. On the screen is an excerpt from a detail in a structural set of drawings depicting the anticipated movement in the exterior bearing wall from wood shrinkage. Also depicted is the anticipated brick veneer expansion. Once the magnitude of the anticipated differential movement is known, The design team should prescribe how to accommodate this movement. The left detail depicts an example of a compression fitting in the main PVC drain vertical line inside a wall system to accommodate the anticipated differential movement within the wall framing. The photo on the right is a case where the contractor did not follow the provided detail, and the building experienced many disruptive pipe breaks during service. So the building owner undertook a repair project to retrofit the vertical drain lines with the compression fittings. Similarly, the exterior walls that include brick veneer, the design team should prescribe how to accommodate this differential movement. Both of these details shown are from the previously mentioned Woodworks article. Note, as indicated in the red dashed boxes, both details call for a movement joint to be constructed above the sill to account for the anticipated differential movement. Okay, so some tips. As mentioned, the design should account for anticipated differential movement. To minimize shrinkage, the framing design can incorporate special detailing or specify wood which has a lower initial moisture content. The design should prescribe how to accommodate for MEP interactions with the wood framing. Similarly, the design should prescribe how to accommodate for brick expansion where used, and the utilization of different structural materials like steel, concrete, or CMU. During construction, the entire project team should collaborate on a building movement plan. First, the contractor should make sure to protect materials from excessive moisture exposure. Next, get the framing as close to the equilibrium moisture content as soon as possible by drying in the building and activating the HVAC systems as soon as possible. Additionally, staging of construction materials throughout the building will help to preload the framing and to close the construction gaps as soon as possible. During occupancy, property staff should regularly monitor their building finishes for distress or performance issues. Contact an engineer or a consultant when issues arise. Steve will cover the next issue on decay, which is our most commonly investigated issue.
All right, thanks, Lorintz. And while Lorintz did mention that this section will focus on decay, just keep in mind, these same concepts apply to reducing the potential for damage from wood damaging insects. So whenever we're talking about decay, similar concepts apply for insects. So decay issues within the exterior enclosure can occur really anywhere, but are more likely to occur in both horizontal components and components that contain additional exposure, like balconies, decks, and breezeways. And the causes, can come from two sources, including water intrusion from an exterior moisture source, such as rain or snow, or from interior moisture source from condensation accumulation. So good design should really consider the 4 Ds to minimize the risk of water intrusion and potential decay. And these include deflecting any water away from the wood construction, such as with flashings or roof coverings, draining water away from the structure using a positive slope, promoting drying of wood that is allowed to become wet by allowing for air circulation, and finally, the use of appropriate durable materials or preservative-treated lumber when there is a potential for water exposure. So some design-related items to consider with balconies, decks, and breezeways are that problems are typically more significant at the uppermost level, and this is because the exposure to the weather is typically greatest in this area. So designs that incorporate an extended roof cover over the uppermost balcony or deck generally reduce the potential for decay and insect-related problems. Whenever possible, penetrations of wood members through the exterior enclosure should be avoided. For example, rather than extending a wood beam through the water-resistant barrier and into a beam pocket, a face mount hanger can be used to keep the exterior framing member from penetrating the enclosure. And complex detailing created by numerous cladding materials and interfaces and the integration of railing posts increase the potential for problems. And these conditions need to be carefully considered with isometric details provided where necessary to convey the design intent. So the images on the right show detailing from a WJE repair project, and I included these just to show an example of the complexity that can occur even at what may first appear to be a relatively simple interface. So when considering design of building materials such as balconies, decks, and breezeways, the amount of slope of the surface should be clearly specified and account for any potential differential movement conditions, as Lorintz previously discussed. It should be clear whether the slope is to be provided by the structure itself or by the concrete topping. If the underside of the structure is concealed, which it often is in parts of the country, we need to think about providing ventilation if possible to allow drying of this area. And this ventilation can sometimes be complicated by fire assembly requirements. However, a lot of times we do still have options available to allow for this ventilation while still meeting these requirements. So water intrusion related problems typically occur at interfaces or penetrations through the building enclosure. And these may include items such as wall-mounted HVAC units, balcony and deck interfaces, window openings, vent and pipe penetrations. So poor flashing or ventilation detailing can also accelerate problems. So the photo on the right shows a project where detailing issues resulting in water penetrating behind the aluminum frame balcony resulted in damage to the exterior wood sheathing and framing, despite furring strips that were used to hold the cladding away from the substrate to provide both drainage and drying or ventilation. So keep in mind too that the moisture source may be internal and not the result of water intrusion. Condensation related problems can exist within the exterior walls and roofs that result in significant areas of damage and extensive repairs. These problems are often related to design, but are typically exacerbated by construction-related errors. So coordination and sequencing during construction between trades is also critical. This coordination step must ensure proper lapping of the air and water resistant barriers and waterproofing layers, and ensure the continuity of the waterproofing, particularly around wall interfaces and penetrations. So the photograph on the bottom left here shows a situation where the waterproofing was properly installed and sequenced properly before the stair stringer was installed at a breezeway. However, the sheathing was removed by the steel subcontractor because they had an elevation issue, which caused them to remove section of the waterproofing, which resulted in a discontinuity that was difficult to resolve without removal and reinstallation of the stairs. The photograph on the bottom right shows a condition where proper lapping between the waterproofing saddle detail at a floor-to-wall interface and the air and water resistant barrier must occur for detailing to perform as intended. And as you can see at the time of this photograph, an insufficient lap, which typically is 6 inches between these components, was not provided yet, as indicated by the arrow. So during the construction phase of the project, potential problems can proactively be identified and resolved by reviewing the required sequencing between subcontractors. Also by discussing any required temporary protection of critical components, such as waterproofing or roofing, from the work of trades to follow. And most importantly, having a really good discussion of those critical details and identifying any potential issues for resolution by the design team before going into construction. And keep in mind, proactive measures can be implemented that help both proactively and reactively resolve issues. And these QA/QC efforts include things like third-party observations, water testing, and even special inspections. And some people in California know that these special inspections have been implemented to be performed, to basically reduce the potential for construction-related issues and related problems. So a little bit about maintenance to eliminate problems related to decay. first thing I want to note is after the building's constructed, property managers and owners should really periodically review critical components to proactively identify any potential problems. These decay-related problems related to design or construction often don't result in problems immediately, but after several years within the life of the building. All too often, these problems go unnoticed until it's too late, as the photograph to the right clearly indicates. And in many of these cases, evidence of problems often precede more significant damage or collapse that could have been identified through proactive assessments. And in response to catastrophic deck and balcony collapses, some states now require inspection of exterior decks and balconies, including California, San Francisco, Chicago, and Florida. Although the specific requirements for each state vary, the intent remains similar. So prior to developing any repairs, the cause of the problem must first obviously be identified and fully understood. For example, if the cause of the damage is related to condensation, the repairs must not only resolve the damage to the structure, but must also address the design or construction problems that resulted in the damage. This step may be time-consuming and costly, but when not performed, similar problems are likely to occur. So the repair should also consider any code-related requirements. Repairs to address decay can often be performed using the requirements of the existing building code rather than the building code for new construction. The repair approach must also, a full set of repair drawings should also be developed, basically just to clarify the design intent and to allow for proper QA and QC procedures throughout the construction process, giving the person or individual doing that work a clear understanding of how the work is to be done. All right, so in summary, when considering decay-related issues related to wood frame buildings, the design team should always remember the 4 Ds: deflect, drain, dry, and the use of durable materials. They should clearly specify the design requirements at critical interfaces and penetrations, and in some cases using isometric details, and consider and mitigate the potential for condensation-related accumulation within the exterior enclosure. And those causes obviously vary throughout the country and are different, in the north, the west, the south, and so your approach needs to change. So when thinking about the construction team should actively or proactively identify any sequencing or detailing issues, and this is often best done with meetings with the subcontractors, but also within the pre-construction meetings, and also to implement any QA or QC procedures necessary to minimize the potential for construction errors. And even if they do happen, so we can identify those before they get covered and resolve them. And property management and ownership teams should regularly review critical components of the building, such as balconies, decks, and railings, to proactively identify any potential problems, and in some cases even involving a qualified firm to do this work. All right, I'm going to hand it over to Lorintz, who will talk about other common issues.
Thanks, Steve. Another common issue in wood frame buildings, as Steve just alluded to, includes blind fastening into the framing. Examples of this condition include the attachment of balcony guardrails and the installation of exterior siding. The photo on the right shows a typical concrete top balcony. The bottom photo shows the view from underneath the balcony of the guardrail post attachment, with 2 of the anchor screws embedded only in the deck sheathing and not into the wood framing. Note, this condition is also commonly includes water leakage and decay of the adjacent wood framing. Another common issue is inadequate framing bracing. This issue applies to both temporary construction bracing and permanent bracing of both wall and floor or roof levels. A good truss bracing reference for both designers and contractors is the Building Component Safety Information, or BCSI, produced by the Structural Building Components Association. We've included a link to this document in the recommended resources. The last common issue that we're going to discuss today is gypcrete floor topping deterioration. The floor topping is commonly used at the interior of the wood frame mid-rise buildings as both a floor leveler and as part of the floor fire rated assembly. The issue commonly manifests via depressions, unlevelness, or squishy flooring, or dusting at the floor joints. The deterioration is commonly due to low material strength from the improper mixture proportioning during batching or inadequate substrate stiffness, or both. Quality control testing during installation, such as slump tests and material sampling for laboratory compression testing, are rarely performed in our experience. Inadequate substrate stiffness can occur when floor sheathing joints are misaligned or when edge blocking is left out. So to summarize, wood is versatile and an economic building material widely used across the United States. Wood is a natural material. It contains natural defects, and its mechanical properties and dimensional behavior are affected by moisture content. Here's a list of the common issues that we've discussed today and that we commonly experience at mid-rise buildings. Some things that we hope you can take away from our presentation include that the discussed common issues are preventable. Design should anticipate building performance and exposure. Construction should protect materials and install them per specifications and instructions. And property operators should regularly monitor for distress. Investigations of distress conditions should attempt to identify the root cause of the actual issue. And repairs should aim to address the root cause, not just the symptoms. Thank you for your time today, and I'll pass it back to Liz for the Q&A portion of our session.
All right, thank you, Lawrence, and thank you, Steve and Paul, for the great presentation. We've got a lot of questions coming in already. As a reminder, you can type your questions into the Q&A box and hit submit, and if we don't get to your question during the call, one of our presenters will follow up with you afterward. Okay, let's take our first question. My understanding was that decay or rot starts at 20% EMC. 30% is quite a bit more. The 20% number came from APA and USDA. Where can I substantiate this number?
I can take that one since it was part of my discussion. So 20% is generally known as the point at which mold fungi will grow. And I didn't specifically talk about mold just because it doesn't have a direct effect on the strength of wood properties. It's generally agreed that if we keep wood below 20%, mold will not grow. So between 20 and 30, as I mentioned, mold and decay can grow, but it's generally understood that wood does require, basically it needs contact with water to initiate decay. And part of the reason that's important, I wanted to mention that, is because just being in a high humidity environment or just being covered within a building isn't typically not enough to initiate decay. Decay requires a higher level to start, and then, like I said, the moisture content can reduce, and that decay can continue. But the 20% number is the point at which mold will start to grow, and that's a good number to keep in our minds. Anytime that mold starts to grow, I think we always need to watch out for those conditions are conditions that can result eventually in decay. And so it certainly indicates that there's a problem and that we want really all wood to be below 20%. Code defines, or design defines, a dry use condition well below 20%. So if we're at 20%, that's a wet use condition where we'd want to use preservative treatments or something similar to avoid the potential for both mold, insects, and decay.
Okay, our next question. What is more likely to lead to cracks in drywall ceiling? Drywall directly attached to the floor joists or drywall attached to resilient channels?
So I think if they're referring to essentially channels that are designed to accommodate for some movement or sleeper channels and things, I have seen mostly cracks develop more when they're attached directly to the truss, most because that's where it's going to be. You're going to see that actual movement occur. If you have resilient channels that are designed to accommodate for some of the movement, you might not see as much cracking, but depending on the level of shifting and deflection you get, you're probably going to see cracking no matter what. And I have seen those in both situations. They consider if you do have excessive deflections, you may want to see them if it's a precursor for another issue. Just hiding those cracks with channels that might be able to accommodate for some of that movement may not always be the best choice either, if that helps.
Okay, a related question. When jacking excessively deflected trusses, how would you best estimate the load required to jack the deflected truss back into place to ensure you're not overloading the floor system below?
So typically we will rely more on sequencing than really designing for a capacity of the truss. If you wanted to do that, you'd have to essentially, I think, analyze and assess the truss or those uplift forces, making sure that you're not overloading your truss for a reverse loading condition. So you'd have to do the actual analysis, knowing the capacity of the wood, the capacity of each plate connector to determine that. So typically we will mostly rely on the contractor who's skilled at doing this to sequence this properly, to go slowly. And once they close those gaps, you're kind of at that zero marker without adding any additional reversal load on it. And once we get to that point, we tell them to kind of lock it off, and then we'll go from there. You may not always lift the floor back completely level, but the intent is to eliminate the gaps between the member to member.
All right, our next question, is there a code provision for student housing dynamic or party loads, or is that just a rule of thumb to consider in our practices?
I'll take this one again unless anyone wants to jump in, but so ASCE 7 does have some lines in there to accommodate for dynamic loading effects, but it's a very vague line, more tailored towards spaces that are intended to have those sorts of dynamic loading, right? So dance studios, areas that might be dance halls or for wedding venues, things like that. And the intent is that you anticipate those and accommodate them most of the time through increasing the live load capacity, right? Sometimes you may need to do an actual analysis to try to limit the bouncing behavior of the truss that you're designing. You can certainly do that by making them stiffer. But when it comes to student housing, there's no specific criteria in the code or ASCE 7, at least not in the national ones. There might be more location specific to address individual multi-family units that are typically designed for like a 40 or 50 PSF live load static. And so it's up to, I think, the engineering judgment, and that's what ASCE 7 basically passes it off to, whether or not you think those conditions are going to be encountered and how you address them from a static live load perspective. Most of the time, you'll just increase that load. So it is becoming, I think, more and more of a conversation with engineers as we find these conditions and we see these high or mid-rise student housings going up all over college campuses. In that we're seeing more and more of these issues because of that. And so the question will become, do we try to push for that to be in the code for student housing, increasing individual unit loads, or do we still kind of rely on the engineering judgment of the designer to try to accommodate for that as they see fit?
Okay, our next question, are the movements noted in this presentation also typical of cross-laminated timber structures?
I guess I'll take a stab at that one. Yeah, thanks for the question. Yes, they are. And again, I would highly suggest you look at Woodworks. They have a significant amount of literature. And I believe they've hosted a few webinars earlier this year regarding this exact topic. The magnitudes of the movement, the differential movements that occur in these mass timber structures, while not a topic that we wanted to discuss in detail today, it is similar. And so there's some similar detailing, or excuse me, specialized detailing that is needed to mitigate the problems from this.
Okay, our next question. Is there any significant difference in wood materials used 40 plus years ago and today relative to decay resistance?
I'll take this one just because it fits into the wood properties section. I think we should keep in mind, all wood in wet conditions will likely eventually rot. It's more or less the time that it takes. One of the significant differences between wood or wood products is the species. Certain species are more durable. For example, a Doug fir is generally more durable than a southern pine. And to the same idea, aspen, which is commonly used in OSB, things like that, is even less durable. So a lot of times it's related to the species. And in some cases, as we found out, products that tend to hold moisture, OSB does have some voids in it. And we know that those do tend to hold some moisture, plus the fact that it's generally manufactured from non-durable species or not as durable species, I suppose, such as aspen, kind of combine, making it a little more susceptible to decay. But I'm not aware of any major differences just because of the older growth timber. There may be. I'm not aware of any, but I think the bigger factors are probably just the species and the type of construction. The glues or adhesives used in engineered wood products don't contribute to the decay resistance, the lack of or resistance.
Okay, we've got time for one more question. Is there an age of building when these types of distress inspections should occur, not related to balcony inspections?
I'll try to answer it, and I'm guessing all of us could easily weigh in, or as many people on the call could. I would suggest any age. So as soon as a building is occupied, I believe Steve mentioned inspections or walkthroughs should just be a regular part of operations. We regularly get involved with buildings during construction, shortly after construction, or after many years of service, and any of them could have issues that we've discussed today, could have the same issues. It depends on the environment, exposure, the detailing, etc. So if you're a building operator, I would suggest at any point, at any age of the building, implementing a routine to just walk and look for issues, as well as surveying residents for operational issues in their units.
Okay. Well, thank you, Lorintz. Thank you, Stephen. And thank you, Paul, again, for the great presentation. And thank you all for joining us. We hope it has been educational. So again, thank you so much for your time, and we hope you have a great rest of the day.